Right, I guess we can start. Yeah, so essentially, I don't have that much important stuff to talk about today, like all the key ideas we already discussed in the last two lectures. So this lecture, I'll just outline some of the odds and ends that I left out, and without getting into much of the technical details. And then we'll end with just yeah, some outlook on some future directions and further problems, things like that. Right. Okay, so the first thing I want to talk about are the system of cutoff functions that we'll need. And this cutoff machinery is essentially needed because of two things. So one is the geometric lemma. Let me call it geometric lemma that, say, Camilo mentioned, requires your Reynolds stress R to belong in a small ball or some ball of some radius around the identity matrix. So let me use my notation. So I'll already have added in this pressure term. So you need this. And this, you can see, is already quite difficult if R is intermittent. So R, it has good estimates in L3/2, but in L infinity, it basically has no good estimate. So it's kind of impossible to have this. So that's why we introduced this intermittent pressure, but still there is some degree in which it oscillates. So that's why we'll need to have some system of cutoffs for that. And the second reason, which is by far like the more non-trivial one, is in order to mix good estimates on the transport error, remember we had to flow the building blocks with the vector field. And in order to flow, you need a flow map, which is basically a diffeomorphism goes from the torus to itself, right? And this depends on time, which satisfies the following PDE. That is, it is flowed by this velocity field. Right? And we need this flow map to satisfy good estimates, simply because in order for our cancellation, we still require these Mikado flows, these pipe flows to still have a well-defined direction in order to apply the geometric lemma. So we basically want phi t to not move stuff so much. More precisely, what we'll need is gradient phi t should be close to the identity matrix. Right? And in order to achieve this, we can only run this flow map, this flow map for a very short amount of time. And the short amount of time, just by transport estimates, so on the transport equation, so these tell you that you can run this flow map as long as for 0 less than t less than something which depends on the Lipschitz norm of the velocity field UQ. And this here is again problematic because we had in our estimates for the transport error, when we had this term, we replaced this L infinity norm by the L3 norm, and then we were able to get the good estimate. But if we were actually to use the L infinity norm in order to run this flow only up to that and then cut it off, then our transport estimates would be horrible. So we'll need to take our velocity field UQ and then divide it up into regions where you have L infinity control. and then run our transport estimates there. So that will be the first thing we do. So let's call this velocity cutoffs. So this is a bunch of functions, so I'll call them psi iq. And psi iq has the property that if I take my velocity field uq, and if I restrict it to psi iq, then the L infinity norm is given by something which is basically the L3 norm of this, so which I will write as, yeah, let me just rewrite it, delta q 1/2. Sorry, let me put a nabla because we are interested in the Lipschitz norm. Lambda q, q minus n bar negative 1/3. So this bit I'll call tau q, which remember was what we used in the transport estimate, in the transport error. And now we have this parameter I, and so we'll put a gamma q to the I. Yeah? No, sorry. No, this R in the geometric lemma, as say Camilo wrote it, is some fixed number. So maybe I think a half is sufficient for this or something. Yeah, thank you. Sorry. Yeah, this has nothing to do with the intermittency. But I mean, as Camilo said, like, and this is something we use, but I won't really talk about it, is in the geometric lemma, you have the identity matrix here, and you can have a convex or a positive linear combination. So any matrix, any two tensor here can be written as a positive linear combination of basis vectors. And then you can really extend it to this entire cone. And what you need to avoid is degenerating near the origin. So you'll need to cut it off somewhere here. And so you'll only be looking at this quantity when it's L infinity norm, or yeah, not when it's L infinity norm, when it's pointwise at every point in this cutoff is between this and this, because then you can apply it. If you have something degenerating, then because we are taking the square root in order to find our coefficient function A, you'll have bad estimates here. And so that's why we need to have some cutoffs even for this. Okay, so you can think of this as just a diffeomorphism from a manifold to itself. The other way of thinking about it is, I mean, you just make these periodic functions of both. I mean, so first write this into R3 and as a fundamental domain, which I guess you need to check that this can tile, and just let's tile it, and this gives another map, T2 to T3. But yeah, all right. Okay, another way of thinking about it is if you just have a vector field on T3, then you can just extend it to a periodic vector field on R3, and now the flow generated by that will produce a sequence of diffeomorphisms which is still periodic. And so it actually, it actually descends to a diffeomorphism from T3 to T3. All right, any other questions? Okay, so we have this, and this is our an additional parameter we are going to use, which basically quantifies how much we are deviating from the L3 estimate in L infinity. Okay, so that's that. And the important thing is this one, you can now get estimates on this. So you can say W psi iq, its L1 norm, is something which is just given by Chebyshev. So maybe I'll leave this as an exercise to you. So essentially what we're doing is we're taking this function, the absolute value of nabla u hat. We know its L3 norm is something, And we are now just decomposing it into sets where it's approximately something like this. And now I'm asking you, because you know it's L3 norm, can you actually tell me the measure of these sets? And so that's the L1 norm of these cutoffs here. All right, so that's one thing we'll need. And I guess another important property, so this is a remark, which ties back into the pressure increment we talked about last time, is that because the velocity field UQ can be is controlled pointwise by the pressure increment, you have the following. You can say that tau Q inverse, sorry, this is tau Q inverse. Then, yeah, gamma Q to the I, psi IQ is controlled pointwise by this pressure increment, by QQ. And I think there's a factor of intermittency. So the pressure increment actually pointwise controls all of these guys. But this is just a remark. Okay. The second sequence of cutoffs we need are, okay, so we have this on which we have good L infinity norms on, so yeah, good estimates on the Lipschitz norm of our velocity field. And so now we can define our flow maps. And we need to cut them off at some scale. So for this, we have time cutoffs. So these guys are functions which I'll call chi I, k, q, where I and q are basically the same parameters there. But the idea is if this is time and this is 0, now k will belong to the natural numbers, and essentially it will demarcate the times. So this will be, let me call it t1 or t, and then or ti. This will be 2 ti, 3 ti, and so on. And ti is the time scale associated to this here. So it's basically this inverse. So it will be tau q gamma q to the negative I. Yeah. Yeah. Yeah, these are cutoff functions in space-time. So yeah, maybe I should write that. So this is from r cross t3 to like basically 0, 1. This is UQ if I restrict it to, sorry, thank you, to the support of psi IQ. Yeah, thank you, sorry. So it's basically, it's a partition of unity. I guess I forgot to write that. So if I sum from I equals 1 to, and there'll be a maximum I. And the maximum I is given by, if you take this, when this matches the L infinity norm. And I guess, and the L infinity norm is basically, if you remember, the L infinity norm of UQ hat is like gamma Q, I can't, it's lambda Q, gamma Q. I think it's essentially this. All right, so if you try to see what's the largest possible I, so that, I mean, the I for which this quantity equals that will give you the maximum I. And after that, like, yeah, because that's the L infinity, that's the global L infinity norm, you won't have anymore. And I guess this is also a nice exercise, is maybe I'll write it here, exercise. Show that this I max is independent of Q. So this I max is actually some fixed constant in our scheme. Okay, so that if I take the psi I cube, and because our cancellation, we want this to disappear, so it will either be raised to the squared power or to the cube, depending on whether this appears in the perturbation used to cancel the Reynolds stress or the current. Okay, but let's concentrate just on the Reynolds stress, and here we have this partition of unity. Yeah. Yeah, but the point of the exercise to show is that it doesn't depend on Q. Yeah, so you can calculate I max by computing these two quantities, and you can show that there's an I max which doesn't depend on Q, for which if I take this to the I max, this will beat this. It's again, yeah. Okay, so we were here. So this K is basically some integer. Yeah, so maybe I should say not R, but R positive. Yep, it's some integer. And what this chi ikq is, it's simply some cutoff function which is supported in a neighborhood of this guy, so that if you add all of these guys up, it's again a partition of unity. So this is basically what is chi, it's around 2, I2q, this will be chi I3q, and so on. So that is this, and on each of these, we'll now start a flow map. So we'll define phi I phi kq to be something that satisfies this equation. And then if I take it at the time given by this ti, so k times ti, this will be just x. So it's the flow map, which is basically the identity at this time, and then you're just flowing it for this amount of time and then cutting it off. All right, so those are the time cutoffs, and these time cutoffs will always come paired with a velocity cutoff, because only there the estimates on this flow map, I mean, only there you have good estimates on this flow map. Outside, you don't have good estimates on this. All right, so that's 2 sets of cutoffs. Now we have pressure cutoffs. Okay. And these guys are used to deal with this first problem. So again, you'll have a bunch of cutoffs, which I'll call omega jq. And it has similar properties to this, but now it's essentially, it's not something that gives a level set decomposition of uq hat, but of pi q. So it's essentially something that if, going just by the remark, if I have delta q plus n bar times gamma q to the 2j, this thing is bounded by qq. So it's essentially a level set, taking this level set decomposition of pi qq. So that's this omega j q. And again, you can do a similar Chebyshev estimate for the norm. And maybe actually here, have I written it down? Yeah, maybe I'll just copy this. JQ, and if I want to measure it in LR, this is given by gamma q to the 3, 1 minus j over r. Okay, so this as well can be an exercise. And essentially what you need to do is you need to use the fact that this is something that has a size delta Q plus n bar if I measure it in L3/2, right? And yeah, and since this is like 2J, you'll see that, yeah, you have the 3/2 times 2, and so that's why you get this 3. And this LR comes from the fact that the LR norm is like you have the 1/r outside. So it's really the support of this set where this is approximately this to the power 1/r. And then you can do the computation and you'll get this. So that's another set of cutoffs. Okay. And now you have what we call the checkerboard cutoffs. So these are things that we already saw when we did dodging. Remember, in our dodging, we took our torus T3, right, which is, okay, something with periodic boundary conditions. We chose a rational vector psi, which for simplicity, yeah, for drawing simplicity, let me just think of it as this direction. And then we decompose this into little pieces, right, of side length over here given by lambda q plus 1 inverse, and on the long side was lambda q inverse. So we saw this in the dodging section where we chose one of these like anisotropic cuboids and did our dodging stuff there. So we'll need to kind of restrict ourselves to looking at one of these pieces. And the thing that allows you to restrict to look at one of these pieces are these checkerboard cutoffs. And we already saw these, I mean, one of them last time, and I think I denoted it by zeta there. And so this will be indexed by the direction chi. And like each of these cubes, I'll just index them. I mean, the countable number of, I mean, the finite number of them, I'll give some ordering to it, and I'll call that L. Okay. So that's, this is a set of, again, a partition of unity, which is identically equal to 1 on this cutoff, and then 0 like in like twice. I mean, in a ball of, I mean, in like double the size of this. Okay, so this is so all of these are partitions of unity. So that's this guy. Okay, I think that's now all the cutoffs. Okay, so now maybe we can write down the full perturbation that we use in our scheme. Well, okay, not quite. Let's say the perturbation. Okay, so this was WQ plus 1. Okay, but okay, so two things. I will only talk about the part which is used to cancel the Reynolds stress. There's a different part which is used to cancel the cubic nonlinearity, which Hyunju briefly talked about how to do. So this is just for the stress, and this will only be the principal part. So remember, Camilo said that just if I write this as the usual ansatz, A, some coefficient times a Mikado, this is not necessarily divergence free. So you will need to add a corrector which makes it divergence free. So I won't be writing the corrector, I'll just be writing the principal part. So this guy is going to be a sum. I'll put all the indices on the sum after. Okay, but first what do we need? Okay, first we need to now localize to some place where we can run our flow map. So we need the velocity cutoffs. So you have the psi iq, and then on this you have the chi ikq. So now we have localized to some region of space where you know the L infinity norm of the gradient of your velocity field, and we have localized to some region of time where our flow map has good estimates. Okay. Now I have omega jq, and this guy is our pressure cutoff, which now localizes to the place where you know what pi qq looks like. So that's this. And now you have this checkerboard cutoff, which now localizes you to this small region of your torus, where you can do your dodging, where you can do this placement of these pipes. So you have this, which is indexed by chi and L. Okay. And now we need the thing from the geometric lemma, right? So we need A psi, and here we need basically some matrix. This is the geometric lemma, which says that if you have something, if you have some matrix, let's call it R, which is in some ball of radius, say a half of the identity matrix, then you can write R as a positive combination of some rank 1 tensors like this. Okay, so this is the A that we now write in order to get the cancellation. Okay, so but here this R needs to be something that's in a ball around the identity. So we take this. Yeah, sorry, and also, yeah, so this basically means it's positive definite. So we need something positive definite, which is why the pi comes in. Right? And so this by itself can be quite large, so we need to normalize it by the size. And the size we know exactly because we have this pressure cutoff. So we know exactly what the size of this guy is going to be. So we normalize it by the size associated to this, and that is basically that guy there. Okay? Right. But okay, now when we apply the geometric lemma to this of size tensor psi, it'll throw out this guy. So this is this R here, right? So it'll throw out this guy, which is not what we want. We just want the numerator. So we have to multiply it with this. And remember, this is something which will get the cancellation when we take this tensor itself. So that's why the 1/2. So now when we take this tensor itself, we'll have this squared, and we'll have this squared. And this squared, now when we sum it up, we'll get precisely R, which was this. And then these two will cancel out. All right, so we have this so far, right? And now we have, so all of this was the slow stuff. All of this was, yeah, the slow functions. Okay, so now we'll have our fast function. So remember, the first fast function is this kind of bold-face row that we had in our dodging, which allowed us to do the dodging, which when we did the bundling. So there's that. And this depends again on chi and on L. All right. And now, yeah, and now we also have another bold-face zeta. So this is something I didn't talk about in the dodging. This has to do with dodging the newer, thinner, more intermittent pipes, which I didn't get to. But okay, there's another set of bold-face zetas which are a partition of unity, which basically are the same reason that this zeta was present for this row. So anyway, so there's that, and which again depends on chi and L. And then there's finally your Mikado, which is something we have seen. All right, which has some placement given by the dodging. And now all of these guys have to be flowed by the flow map. Flow map given by phi, and this phi is something which is just a flow map which is on this cutoff. Remember, it's just the flow map which has very good estimates just on the small time interval, and it only has good estimates on this set. But those are already included in the properties here. So now we just have this flow map, QQ. Okay. But this building block is not quite divergence free, so we just need to add in yeah, the transpose of this matrix inside. And these are the fast guys. Right. And so this is our perturbation that we use. And the reasons for all of those are like kind of, most of them are these cutoff functions, which are these just technical objects needing to isolate the correct part of space-time where you have the good estimates. Okay. Yeah, so let's maybe, so there's I, there's a K, there's a J, there's an L, there's the set of directions chi, there's the set of those cutoff functions. Okay, anyway, let me stop. Okay, there are a few more. Whatever subscript is there, we are summing over that, and they have their appropriate. So I goes from 1 to I max, K goes basically like the naturals, 1, 2, 3, 4. Then J goes again from 1 to, there's also going to be a J max. Then L is something which counts these guys. So it's like how many of these are there, and so on. Yeah. Yeah. Yeah, the xi is the finite set of directions. Yeah, exactly. All right, so that's the perturbation. And I guess almost all its glory. Okay, let me talk a bit about the various parameters involved in the scheme. And let's just do an example computation to see how these parameters behave, essentially. Okay, so what are the parameters? So there is beta, which we need to choose, which is the regularity parameter. And this basically is telling you like what L3 based Sobolev space you're going to be in. So if I choose beta to be something less than 1/3, you'll be basically in the Sobolev spaces just below that. Okay, so that's your regularity parameter. There's going to be n bar, which we saw, which denotes how finely you have to cut your frequency. So it's like you had here lambda q, and here we had lambda q plus 1, but we decided to call it n bar and just basically cut these up very finely into n bar many pieces. Right, so that's a parameter which indicates how fine you need to do this thing. There is b, which is the base of your super exponential guy. So this b is something which is greater than 1, but it can't be too far away from 1 for good estimates. And then you can now define your lambda q to be some fixed lambda bar to the b to the q. Okay. And then delta q can be now defined as lambda q to the minus 2 beta. So these are some parameters. And there are two more which, so these are really the main ones. There are two more which are slightly more technical, but it's kind of amusing to think about them briefly. So this epsilon gamma is the definition of how fine you're going to make these gamma q's. So like how fine you're going to like do this level set cutting up. So gamma q is something which will be defined to be lambda q plus 1 over lambda q to the epsilon. Okay, so this will be like really small. Okay, so this gives that. And then we'll also maybe, let me call it capital N, which is like the number of derivatives needed. Needed to be kept track of, or number of derivatives needed in the scheme, let's say. Okay. And let's just do a slightly amusing computation to see how these kind of behave. Uh, yeah, unfortunately, in our scheme, there are a lot more parameters than just this. But in some sense, these give you an idea of like most of the main things. Okay, so let's say we wanted a solution of Euler which satisfies this local energy inequality, and I wanted it to be in the space W some 2/3 minus epsilon. So let's say, sorry, 1/3 minus epsilon. So let me say 0.332, and then in an L3 base space. So essentially, I'm going to choose now beta to be 0.332. Actually, this one, maybe let's say 331, so I just choose beta a bit higher. Right, so this is something less than 1/3. So we can start running our scheme. Okay, in order to do this, the n bar we needs to be quite small. So let's see, what's a good intuition for this? Yeah. So I guess the intuition is, if I look at the error generated by just something at lambda q plus 1, then I need to gain enough. So that kind of tells me what n bar is. And I think it has to basically be, yeah, around 1,000 for this. So yeah, you need to split this up into at least 1,000 pieces. Okay, so that's that. And now B is something such that, remember in our computations, when we saw the oscillation error, say, so this is what Hyunju wrote in the heuristics. In the oscillation error, you had to close lambda q over lambda q plus n bar, and here delta q plus n bar, and you wanted to close it with the next one, so here it's delta q plus 2 n bar, right? And now if you do the computation, or if you look at your notes to what you saw what Hyunju wrote, you get beta will be less than 1 over 3 b to the power of n bar. Okay, so this b to the power of n bar has to be sufficiently close to 1 so that this beta can be this, right? If b to the n bar is very large, then this is going to be very small, and you won't have beta being 0.332. All right, so B is such that B to the 1,000 is kind of like, yeah, like a like 1.001, right? So if you put 1.001 here, I think you'll basically get something like that. So B to the 1,000 should be that. So B will be something which is like, you need to take the 1,000 root of this guy, and I think to first approximation this is 10 to the minus 3. This is again 10 to the minus 3, 10 to the 3. So I think this will be 10 to the minus, sorry, 1 plus 10 to the minus 6. Yeah, I don't know. Is that right? Okay. Anyway, you can check. All right. So I didn't tell you what this epsilon gamma is, but this basically is something like, it should be smaller than, in fact, b minus 1 square for technical reasons. Okay. And so this kind of tells you that epsilon gamma is like, okay, b minus 1 is 10 to the minus 6. So here you'll have 10 to the minus 12. All right. Okay. So let me just check if I'm right so far. Yeah. Okay. Okay. Now let's see how many derivatives we need to keep track of in the scheme. So remember, the number, we saw some bound of the number of derivatives we needed to keep track of when we did this, when we looked at the localized inverse divergence. We had a bunch of terms, and then we said the final term we want to eat up some Sobolev loss. And the final term kind of looked like this. You had a lambda q over lambda q plus 1, and then, yeah, sorry, you were gaining at each time gamma q, and then you raise this to the nth power, so like the nth expansion that you had, and this one you wanted this to beat some lambda q plus 1 to the power, say, 100. So I wrote before just some fixed constant c, but let me just fix some constant. Okay. And so this guy, let's just expand it. So this is, I want lambda q over lambda q plus 1. And so this will be epsilon gamma times n. So I want this to beat lambda q plus 1 to 100. And what does this mean? So this is basically lambda q, right? So this is lambda q, and this is lambda q to the b. So this is 1 minus b times this, 1 gamma n. I want this to beat lambda q to the 100b, right? Because that's lambda q plus 1 is lambda q to the b. Okay, so I want this to beat that. And so if I write that down, so then that means that I need b minus 1 epsilon gamma n to be greater than or equal to 100, basically. All right, so then I move this to this side. Sorry, this is mine. Sorry, this should be a plus 1. This should be this, and so this is b minus 1. So now I need this to be greater than 100 divided by epsilon gamma times b minus 1. Okay, and what was that? Epsilon gamma was 10 to the minus 12. So this is 10 square. 10 to the minus 12 is plus 12. And b minus 1 was 10 to the minus 6. So this is 10 to the 20. So you need to keep track of 10 to the 20 derivatives in your scheme, which is ludicrous, but amusing, I guess. Yeah. All right. So this kind of maybe gives you some feeling of the ridiculous numbers generally involved in convex integration schemes. Yeah, and the fact that they give you a sharp space is kind of interesting. All right. Another thing I just wanted to briefly touch upon is about prescribing the energy. So the local energy dissipation. Okay. Essentially, what the scheme allows you to do is it has the freedom of adding a prescribed, of achieving a solution of Euler which has a prescribed Duchamp-Robert measure. So you can find the scheme actually works if in your relaxed equations in the local energy equation you have the following. So this is something you've seen, right? And now here I'll write equals, and now I have the kappa q, then I have this term, and then I have this term, the current, which is cancelled by the cubic, by something cubic in uq. And then I can add this function e of tx, which is independent of q. And now, so what happens is when I run the scheme with this as my relaxed equation, these go to zero weakly. I mean, these go to zero strongly. So when I take divergence, so if I take some test function and integrate against, this goes to zero in distributions. And so you are left with a solution of Euler which can prescribe this guy here, your local energy dissipation. But in our scheme, ETX is, we can't really prescribe it to be anything. It has to be, for instance, smooth, a smooth function. And yeah, so for instance, you can get like absolutely zero energy dissipation locally. You can have something which has positive and negative. You can have something which is strictly dissipating and so on. Okay, I write this, but I say plus some other derivative bounds. All right, so that's just some remark which I wanted to mention now, because I want to talk about outlook of like what future directions are there and what one can do. Okay. Yeah. It's a smooth function. I mean, like the way Duchamp-Robert defined it for a weak solution of Euler, which is say L3, you do actually get a measure, some well-defined measure. But what we are talking about here is we are only able to prescribe a function, not a measure, which will be one of the future directions, actually. Okay. Okay. So the first problem, I think, that is quite interesting to study is what range of structure function exponents can solutions of the Euler equation have? So can one prescribe structure function exponents, so or regularity? Okay, so let's define a function beta p, which I want this to be the regularity of some solution measured in an LP-based space. So let's just talk about Sobolev spaces, so alpha pp. So I want U to belong in alpha pp. And then if I multiply this by p, this is usually called the structure function exponent. It's simply because physicists don't like to put the 1 over p when having an LP-based space. So that's why this extra additional factor. Okay, and I can draw it here. So this is something I think Ujjwal already drew. And here I have my, I called it beta. Right, so Ujjwal already drew this. So P is like 1, 2, 3, 4, and so on. And here, let me have, yeah. So the main space for Onsager for energy, so the one proved by Constantine ATT, is you want 1/3 of a derivative in L3. So let me call this 1/3. Okay. So if you're more regular than this, you have to conserve the energy, and the Onsager conjecture basically says that if you're less regular than this, then you can dissipate energy. Okay, and the constructions which were, sorry, this is not 1/3, this is 1, because 1/3 times 3 is 1. Okay, the solution that Izzat gave of the Onsager conjecture basically is something homogeneous. So it was based in C 1/3, and it's homogeneous. So if you actually measure it in any LP norm, not infinity, you still have just 1/3 of a derivative. So his solution gave this as the range of structure function exponents. So it was always, yeah, beta p equals 1/3 p. So it was like 1/3 of a derivative in any LP-based space. All right, and this is exactly the same as the K41 expectation. K41 theory of Kolmogorov is also something homogeneous. It has no intermittency, and it tells you that this should be the line. Okay, so But the intermittence scheme, so the one of Matt Novak and Vlad Vikol, so they are able to get H1 half. So that's something which, so H1 half, so it's half of a derivative in L2, so half times 2 is 1. So they get that space, and they have L infinity, but they have no Holder regularity. So they have basically this space, this. And I think this goes down to a half here in L1. So let's say this is Izet. This here is Novak and Vlad Vikol. And our solutions are L3 based, and so, and they're L infinity. So basically you copy, you have the same thing here, but now since we are measuring everything in L3 and we need this cubic movements to be bounded, we can't really get good estimates in L2, so our thing just goes down like this. So we just get 1/3 of a derivative, so everything below 3. So this is the scheme that we, that was presented over the past few lectures. Okay, but the question is this, and it's motivated by actual turbulence, what we see in experiments. So in actual turbulence, in what we see in experiments is that if you measure like the regularity of a turbulent solution in L2, L3, L4, you can map these structure functions out, and what you see is a curve that kind of looks like this. Okay, I don't remember where it is in L1, but in L2 it's something which is above a third, but not quite a half. It kind of gets close to this point, so people expect it to pass through this point, but again, there's some recent debate about whether it actually does so. And then it does something like this. So it's some concave, I think. Concave function which goes like this. And again, the behavior at infinity is like, we can't really measure, like, I mean, like experiments and numerical simulations, if you ask them to measure the L20 norm, like it's impossible. So we have kind of this curve, but we don't know what its behavior is. And this is what actual turbulence is supposed to look like, this curve. But mathematically, like convex integration should give you a lot of freedom. So like a question you can ask is, and this is probably the most ambitious one, you can form less ambitious ones, is I give you a curve, let's say it's piecewise linear, or even smooth, or something. So some curve like this, which is say convex, some arbitrary curve. It did not even pass through this point. It can't get higher than any of these guys, just because then you'd have conservation of energy, and then we don't know with convex integration to produce any such solution. So there's some restraints, but modulo those restraints, I can just give you some curve. Maybe it does this, then does that, something. But I just want it to be convex, concave, going like that. And can you construct for me a solution of the Euler equations which has this regularity? So if I measure it in, say here, L5, I get something. If I measure it in L3, I get something else. And yeah, so it has exactly this regularity, or yeah, arbitrarily close to this regularity in the LP base space that you want. So this is, I think, quite an interesting question and should demonstrate really the flexibility of what you can do with the Euler equations. I don't actually know what to expect here. There might be some restrictions, but yeah. So this is something which is very tantalizing. Well, it doesn't need to. I could have chosen the blue line to pass below it as well, and that would be equally interesting. This is just like the kind of the one which physicists and turbulence people really care about, so that's why I just made it pass through that. But yeah. So that's one question. And yeah. Yeah, alpha 4, I'm telling you should be something. And then can you actually find such a solution of the Euler equations that does that? Yeah, so here there's no local energy inequality, and this is just the usual, just the the divergence-free condition and the momentum equation. I just want a solution of the incompressible Euler equation, so that has this. Okay, and the second question, maybe I'll write it here, is, I guess, what was already asked before, which is, can one prescribe the Duchamp-Robert measure? Okay, and this seems, I think, much harder. At least for this, maybe there'll be some heuristic estimates you can run to try to see, like, if, yeah, range of flexibility afforded. Here, this seems much harder. So here, the question is, I'm giving you some measure, say mu, which depends on space and time. And, okay, maybe I'll write it as subscript, which has a sign, say, is positive or non-negative. And I'm saying that, does there exist a solution of the Euler equations, of the incompressible Euler equations, that has this as this dissipation measure? So here, actually, it's very interesting. There are very recent new works which are imposing, which are producing rigidity results. So I guess, okay, I might be wrong in what I know about history, but there was this paper of Constantine ATT, which showed that if you're above b 1/3 3 infinity, so more than 1/3 of a derivative in L3, then you conserve energy. So that is like this, the rigidity part of the Onsager conjecture. There were some extensions to this in the 2000s, but there's some very interesting recent work by, I guess, let me mention this work first. So by De Rosa, Luigi De Rosa, Theo Drivas, and Marco Inversi. And they show that if you have dissipation in the Euler equations, then this can't be supported on a small set, basically. So they have a lower, so I think they're able to bound the Hausdorff dimension of the support of mu. So they show that this has to be larger than something, which I can't remember, something larger than 0. And so they say that if your dimension of this support, of this measure is actually less than this threshold, then you actually conserve energy. So this is like, in some sense, a rigidity result, which incorporates the geometry of how the dissipation can take place. And there's another very interesting result by Luigi De Rosa again, and Phil Izzet, which show that if this, so let me call this D or gamma, if gamma is non-zero, if gamma is not the whole thing, so if gamma is strictly less than 3 in this case, so we are in 3 dimensions, so let's say gamma is strictly less than 3, this, and you have dissipation happening, so this is non-zero on a, this is positive on some set of some Hausdorff dimension which is strictly less than 3, then you must have intermittency. Then one must be intermittent. Which is basically to say that if your dissipation set is something not full dimensional, then you can't have this line as your prescribed structure functions. You can't be 1/3 of a derivative in all LP base spaces. You need to like have some intermittency and go below that, which is in some sense very interesting from the point of view of I guess fluids, which is okay, fine. For instance, a corollary would be if you do solve the strong Onsager conjecture, so for C 1/3 base spaces, then for that you cannot prescribe the dissipation measure, so this ETX to just be some measure supported on a lower dimensional set. It has to be supported everywhere. Supported on a full dimensional set. Sorry, not supported everywhere, supported on a full dimensional set. And yeah, so these are very recent new results towards rigidity in the Onsager conjecture, or like this now local version of the Onsager conjecture, which tells you some bounds on the geometry of how this dissipation can take place. And it's a very interesting question now to see how sharp these things can be. Like if I give you some measure or something which does not violate these conditions, say, then can you actually construct a solution of the Euler equations? So this is in some sense a very new like the Onsager conjecture kind of on steroids. It's like now you have much more rigidity results known, and you want to ask if they can be sharp, or like what exactly is the threshold of regularity here. Yeah, so I think this looks very interesting questions here. And yeah, I think I'll stop here. I don't have anything else to say. Yeah. Yeah. Yeah, that would be one question one can say. So that doesn't violate any of these conditions. If it's supported on the whole space, some measure, even if it's not C infinity, that's already quite interesting. So say you had some function with some discontinuity, some jumps, then even that, like our scheme doesn't work for that. And so it would be interesting to see how to adapt or like do something new to deal with that question. Yeah, so that is open. Yeah, this mu is the dissipation measure. Maybe I should have called it something else. Like I think this is Duchamp-Robert's notation. Sorry. Yes. Can I prescribe this guy? That's the question. Well, it doesn't need to be non-negative. You know it's non-negative if it comes as the vanishing viscosity limit of Navier-Stokes, right? I mean, our solutions, we can have this ETX to be negative and positive. You don't know it's non-negative. So actually, I can even remove this, but I just kept this. Yeah, I mean, the physically interesting case is when this has a sign. Yeah, and there is some rigidity. Yeah, so yeah. Yeah, I have no conjectures here about like what could be sharp and what, yeah. I don't know how physicists or like fluid dynamicists do experiments in numerics, but I guess like in experiments, they measure like correlations. So like 2 points close by, and then you can measure fx minus fx plus h. And now you're raising this to the power p. And then you see how this quantity behaves as you vary p. Like if you average, if you take 2 points and then let the fluid flow for a very long time, and now you have this time average of this quantity, and maybe you do something. Yeah. I should mention that. Yeah. Yes. Right. Yes. Yeah. I mean, yeah, you need to put a force because otherwise, if you have dissipation, then the energy will go to 0 to 10 to something. Yeah. Yeah. Right. Exactly. And then you ask for that. Yeah. Yeah, exactly. And in the numerics, you can run any sort of some numerics and do basically the same thing as you do in the experiments. Then you get these graphs, which are very tantalizing. And if one is to believe that turbulence is universal, then this graph should have, the one you actually see in nature should have some very deep meaning. I don't know.